there. Welcome to Math with Sittig. I am going to, in this video, talk about simplifying rationals. At some point in the not too distant future, I will also do a solving rationals, and I'll also do a solving radicals. But the best place to start with rationals is simplifying them. I'm going to start with a couple of different types that you'll see. The first one is the most basic, simplifying rationals, where it's monomial over monomial. And if you have done division already in your lifetime, then it'll feel very familiar. So say I have something like 6x to the 4th over 3x to the 5th or something like that. Okay, this is still technically a simplifying rationals. What you do is you deal with each piece individually. All right, but before you go to factor or reduce anything, you want to find your, they call them, I've been calling them restrictions, but that's not the only word for them. Sometimes people will call them excluded values. What you're looking for is what would make my denominator equal 0. Okay, because in the land of math, one of the few things that you are never allowed to do is divide by 0. When you divide by 0, you get an undefined answer. If you are graphing something like that, it means that there's a hole in the graph or there's an asymptote in the graph, and you just can't have that. So the idea here is I can never let this be equal to 0. So what I'm going to do is I'm going to go ahead and I'm going to set it equal to 0. I'm going to solve, right? I call this a restriction. I'm sure there are millions of other names for it. So I'm going to divide both sides by 3. So I get x to the 5th equals 0. Now you might not have done a 5th root, but the rule applies the same with squares. So if this is a square, you get rid of it by square rooting. If this is a third, you get rid of it by third or cube rooting. 4th, 5th. So if this is a 5th power, I can get rid of it by 5th rooting both sides. The 5th root of 0 is just 0. Now, here's the trick. This is not an answer. This is now a restriction. What that tells me is I am allowed to plug in anything that I want for x. Like if I want to see what this looks like in a graph, I can plug in 1, I can plug in 7, I can plug in -4, I could plug in -6.83. I can plug in whatever I want. But what I cannot plug in or substitute in is that number right there. Because if I did that, it would take this denominator and make it a 0, and you can't divide by 0. Okay. So now that you have your restriction, and this is a basic problem, and you'll see they'll get a little harder as we go, what you do is you divide like term by term. In this case, it's monomial by monomial, so I have a coefficient, numbers, and then I have variables. So I take 6 divided by 3. 6 divided by 3 is 2. The 6 is on top. It's bigger, so the 2 stays on top. X to the 4th divided by x to the 5th. Several ways to think of this. Okay, x to the 4th over x to the 5th. The x's divide to 1, so they reduce, but they have to match exactly. So notice on top I had 4 and on the bottom I had 5. When they reduce, I'm left with 1 and it's in the denominator. So this would reduce to 2 over x. The other way you could think of it, the generic rule says what you do is you take the power on top minus the power on the bottom. That gives you x to the -1st. If you're in my current class, we haven't seen this yet, but if you've taken math with me before and taken algebra 2 with me before, I don't know why you're watching this video then, but if you are, what you should hopefully remember from algebra 1 is that this negative power means that it's in the wrong location. So what happened is I solved this and I thought, oh, okay, x to the -1. Right now it's living in the upstairs of the apartments, and it doesn't want to, it wants to live in the basement. When it moves to the basement, it becomes a happy +1, okay? If it is in the basement, unhappy power, it moves upstairs. Only the power creates the movement there. So if you aren't 100% sure about this yet, just think of it as the expansion. Or back here, you see I have more x's on the bottom than I do on the top. So when they reduce, I'm left with x on the bottom. All right. The next style that you see, and this is the one that catches a lot of my students because people just don't like GCF for some reason. The next type you might see would be something like, I don't know, 12x minus 24 over, let's do 5x minus 10. All right. Now this one is a little bit different of a process because the first thing that you want to do is you want to factor. So before you do your restriction, this is going to become step 2. Step 1 is going to become factor. And for pretty much every rational after this, that's what you would do. This one didn't factor, which is why we didn't bother. But anytime you have binomials, trinomials, any of that, you generally want to factor. I also, because I am a little bit of a control freak with math, I like to put parentheses around anything that is not a single term, because I want to remind myself and every human that sees this or sees me or hears me that just because there is an x here and an x here does not mean that I'm allowed to reduce those, because this is 12 times x and this is 5 times x, and those are not the same thing. And in fact, this isn't just 12 times x, this is 12 times x minus 24, and this is 5 times x minus 10. These are not the same thing, and just because they both have x's doesn't mean you can reduce them. All right. The reason that this one throws people off, like I said, is people are not as into GCF as they are into other types of factoring. But what I do, because I see this is not a squared, and because you should always check for GCF first, I'm going to check GCF. 12x and 24 can both be divided by 12. So what I'm doing is I'm factoring or dividing that 12 out to the front. They don't have an x in common. They don't have anything else in common. So now what I have in the parenthesis is what I would have before distribution, or when I factor. 12x divided by 12 is 1 with the x. You can write 1x if you want. You can just put an x. They mean the same thing. And then negative 24 divided by 12 is negative 2. Okay, top is factored. Now I go ahead and do the same thing for the bottom. 5x and 10, the biggest thing they have in common is 5. When I divide 5x by 5, I'm left with x. When I divide 10 by 5, negative 10 by 5, I'm left with negative 2. Okay, I made this one work out so I could do some reduction. Before I do that though, and this is the key, if you reduce and then you try to do your restrictions, you will miss your restrictions. Okay, it doesn't matter that the x minus 2's match yet and that they're going to reduce each other, which we're going to look at. We still have to look at this denominator and find our restrictions first, because we don't care. I mean, we care what it looks like at the end, but the problem is it has to work back at the beginning too. So we need to make sure that whatever x we want to plug in is not going to create an issue. All right, or if you graph it, like I said, it'll either create a hole in the graph or it'll create an asymptote depending on your factoring, which that's another story for another day when we're talking about graphing. So now I'm going to take just the denominator. I don't care about the top. We can divide. We can have 0 on the top. We just can't divide by 0. I'm going to say 5 equals 0. When does 5 equal 0? Never. So that doesn't do anything for me. This plain 5 does not create a restriction. Okay, x minus 2 equals 0. I add 2 on both sides. So my restriction is I can't plug in 2 there unless I want an undefined. If you have a graphing calculator or you have access to a graphing calculator, go ahead and plug this into your graphing calculator, pull up the table, and what you'll see is at 2, it will read, most of the time it'll read as error. Sorry, I'm fighting a lamp again. All right, step 1, factor, check. Step 2, find your restriction, check. Step 3, reduce. Step 4, profit. Okay. Now, the trick with reduction is you can only reduce what matches exactly between the top and the bottom. So here, the 12 and the 5 don't match exactly. Because they're both numbers, though, I am allowed to reduce them. However, 12 and 5 don't have any numbers in common to divide. They don't have any factors in common. So the 12 and the 5 are going to stay. This x minus 2 can only reduce if there is another matching x minus 2 on the bottom. If this said x minus 4, if this said x plus 5, if this just said x, you couldn't reduce it. It's the fact that these two together, how many times does x minus 2 go into x minus 2? 1 whole time, so they reduce to 1. When I multiply by 1, though, it doesn't change anything, so my reduced polynomial is 12 over 5. Okay, do you see, though, that if you didn't get the restriction back here, you would get to your answer and be like, oh, there's no restrictions because this is just a 5. But there's a restriction, and it comes all the way back from the beginning. You find it best when you factor. All right, one more example of this, and there are many, many examples, so if you want a more intense one than this, then you can let me know in the comments below. Same steps. This one just has a slightly different factoring form. So it means I have to come up with some factoring. So let me think for a minute. What if I did x squared minus 36 over All right, I think this will work. If not, we'll come up with a new one after I check it. All right, because I am who I am, I'm going to put them in parentheses because I don't, and I see, I rant about it. And I still, when I give a test on this stuff, will have students that are like, oh, x squared, psh, done. No, you can't do that. All right, just because they look the same here, remember this x squared, once you square it, is then having a 36 subtracted. This x squared is then adding an 8x, which would also then have a number, and a 12 to it. So they're not equivalent, so you can't just start marking off pieces. You can't say, oh, 36 and 12 reduced, so I'm going to reduce there an x squared. Don't do that. So you have to factor. The top is a difference of squares. If you need to see a factoring special forms, I have a video on factoring special forms. The bottom is a trinomial with a 1 in front. I have a video on how to factor that if you need to see it. Difference of squares, you square root the front, you square root the back, one gets a plus and one gets a minus. This one you factor 12, factors of 12 are 1 and 12, 2 and 6, 3 and 4. The ones that will add to 8 are 2 and 6. Pick that out cleverly so I'd have some reduction, but not all reduction. But before I reduce, I have to find my restriction. So step 1, factor. Step 2, restrictions. This will have 2 restrictions because I have 2 binomials on the bottom, so I'm going to take each of them and set them to 0. I need to find out what would happen if x plus 2 was 0, or how I would get that, and how I would get to x plus 6 equals 0. So I cannot let x be negative 2, because if I let x be negative 2, it will be undefined, or it will be an error if you see it in a graphing calculator. That means in the graph, it will either be a hole, or it will be an asymptote, all right, depending on the power, depending on the life power of it, not like it's power. All right, minus 6. So I have 2 restrictions. They are part of my answer. If you do not include a restriction, then you do not have a full answer. Okay? Now that I have my restrictions, I go ahead and I reduce. I look for what matches exactly between the top and the bottom. Now notice, I have an x minus 6 and an x plus 6. They are alike, but they are not the same because this is a plus and this is a minus. I have an x minus 6 and an x plus 2. Not even close. I do, though, have this x plus 6 and this x plus 6. It doesn't matter that they're not right on top of each other because they're multipliers, so I could rearrange them if I wanted, because multiplication is commutative. These two are going to reduce each other to 1. 1 multiplying isn't going to change anything, so you can multiply 1 through if you want, but we just kind of ignore it. And we get x minus 6 over x plus 2. That's our final answer. It is the reduced form of this. But what you have to include are those restrictions, all right? Because when you graph this, it's not going to look the same as this, like in a calculator, because your calculator doesn't understand that you reduced it from this. So your calculator is going to miss the restrictions. But if you graph this beautiful thing, it is going to have restrictions. All right, so that is a kind of a small version of simplifying rationals. I didn't include any major factoring materials, so I didn't include any cubics, and I didn't include when you had a number in front of the x squared. That will happen. That does happen. I can do a video on that if you need it. But you now have simplifying rationals, okay? At some point in the not too distant future, I will do a solving rationals and a solving radicals. All right? I have all sorts of factoring videos. You can subscribe. You can not subscribe and just search them. You can like this video if you're super into rationals. But I have factoring, I've got quadratic, I've got completing the square, I've got imaginary numbers now. Here's the simplifying rationals, all right? They're all up there, and if there's anything else you need, you can comment below. And I hope you have a lovely rest of whatever time it is that you're doing with whatever it is you're doing with your life. Hopefully math. No math homework, please do the math homework. All right.